This is Unit 4, Video 6. In this video we will talk about solubility, how and why compounds are soluble. Now, we'll define solubility as less than 0.01 moles per liter. And what this means, this is 1/100th of a mole, not much. 1/100th of a mole could be just a small amount on your hand, depending on the compound, of course. But this will be the break point between soluble and not soluble. And here we have a compound that we've dissolved in water, and that is called then a solution. A solution has a compound dissolved in water. If you have what's called a suspension, that means it looks cloudy, and you have little particles that are actually hanging in the solution. Now, this one will be clear. You will be able to see right through the solution. This one will be cloudy. That's why a cloudy solution really is not a solution. It's called a suspension. Eventually, that suspension will settle and create a precipitate. And this precipitate is the insoluble solid. This is the solid that we've seen in precipitation reactions, and we'll see again quite a bit. Now, there are rules for solubility. We call them solubility rules, and you must memorize these solubility rules. There are a few major ideas that you have to keep track of, and let's show you what those are. So, for the soluble compounds, if you have a group 1 metal ion, these are alkali metals from group 1 on the periodic table. Here's the periodic table, so it comes from this group right here. Then they will always be soluble. There are no exceptions to these. So, for example, compounds like sodium chloride famously has sodium group 1. That's always soluble, no exceptions. Potassium iodide, rubidium, anything you want, really even rubidium carbonate will also be soluble because you have these group 1 metal ions. Okay, likewise with this polyatomic ion, this is ammonium. Remember, ammonium is one of those polyatomic ions that's a positive. It's one of the few positive polyatomic ions. There are also no exceptions for ammonium. All ammonium compounds, for the most part, are soluble. Another famous one is nitrate. This is actually extremely important. All nitrates are soluble, no exceptions. So anything nitrate, so for example, if you have calcium nitrate, you have two of them. If you have cobalt nitrate, if you have nickel nitrate, if you have iron nitrate, even if you have iron 3 nitrate, for example, all these are soluble. Because of the presence of nitrate, they are soluble, which means they will dissolve in water. Another one with no exceptions is acetate. This is acetate, also important. And then you have chlorate and perchlorate, the 2 polyatomic ions. So there are no exceptions for any of these. So any of these compounds that you see, any of these polyatomic that you see in a compound, the compound will be soluble. So for example, you see yourself, say, magnesium chlorate. You know that it contains one of these soluble compounds, so this will be soluble. Now, if it is soluble, what we will do is we'll put a little aqueous behind it if it's soluble. So all of these, for example, will have aqueous as their state in the reaction because they are soluble. Next, we get down to something that has some exceptions. So group 17, so you can say that between here and here, there are no exceptions. But if we break apart these two, we actually are encountering some exceptions. Group 17, remember, are the halogens, and the halogens sit in right next to the noble gases right here. These are the noble gases. So group 17, compounds for the most part are soluble. So like any chlorides, any iodides are soluble unless you have one of these 3. Now I call these 3 the 3 robbers, just for you to remember them better. So if you have silver that encounters chlorine, silver chloride, then will be a solid. Oops, that's a chloride. Will be a solid because it is not soluble. It's an exception to the solubility rules. Lead is also in the same category, and so is mercury. So, for example, if you find yourself lead iodide, PbI2, lead 2 iodide, this will also be a solid. But iodide, anything else, iron iodide is aqueous. Iron iodide is aqueous. If you have titanium iodide, titanium chloride, all of these are aqueous. Aqueous, aqueous. So the rest of these are going to be aqueous. And that's what we mean by soluble or insoluble. Then the last one that has some exceptions is sulfate. This is pretty important as well. Make sure you know this one. Sulfates are also generally soluble unless you have the three robbers. Here they are again, just like above. And then these I call the three bandits. And think of Ba for bandits, barium. These are actually group 2 metal ions on the lower side. These are the alkaline earth metals from calcium down to strontium. However, here it says calcium is on the border, so some people say that calcium technically is soluble. Okay, so for example, if you have barium sulfate, this will be a solid. If you have strontium sulfate, it'll be a solid. If you have silver sulfate, this will be a solid. That's how it works. But sulfate, anything else like iron sulfate, copper sulfate, those will be aqueous. So we're going to apply these solubility rules, but we're going to show you one quick slide of stuff that is insoluble. Now, what we do is we consider everything else as insoluble, not soluble. We're going to put a little solid behind it. So, for example, if you have carbonates, if you have phosphates, any other polyatomic ion will be insoluble, except these two are usually mentioned. Sulfides are usually insoluble. So, for example, if you have yourself iron sulfide, FeS, this will be a solid, not soluble. Most sulfides are not soluble, except with the three bandits. Notice the three bandits appear here again. And same thing with hydroxide. Most hydroxides are insoluble. So if you have iron hydroxide, iron 2 hydroxide, for example, this will be a solid unless you have barium, strontium, or calcium. Again, these are the three bandits. And obviously, here it says, if you have anything from group 1, obviously that will always be soluble. That is from the previous page. So the thing to do is actually to practice these solubility rules by applying them to example problems. And let's do exactly that. Predict whether each of the following compounds is soluble in water. So in this case we have potassium phosphate. We have to ask ourselves, do any of these, now all these are going to be ionic compounds. The solubility rules apply for ionic compounds. So you'll essentially break the compound up into a cation and an anion and ask yourself, is this soluble and is this soluble? Now potassium is a group 1, and the first rule says all group 1 metal ions are soluble. So this one will be aqueous, which means it is soluble. So we'll put a little check mark, a little AQ behind it. Okay, the second example has nitrate and cobalt. Now nitrate was another one that's always soluble, no exceptions, always soluble. So this one will also be soluble, and we'll put a little aqueous behind it. Now, the next one is hydroxide. Now, gallium hydroxide, you can either take a look at this one or this one. Now, we mentioned hydroxides as being insoluble, however, they have a few exceptions, the three bandits. Gallium is not one of the three bandits, which means this actually is not soluble. Most hydroxides are not soluble, is the idea. So this gets a solid behind it. How about silver bromide? Now here we have a group 17 ion, halogen ion. So we said that group 17 are always soluble except three exceptions. So they're not. So they are soluble except the three robbers, and silver is actually one of the robbers. So because it's a robber, it makes an insoluble compound. We'll put an S behind it. Next one is barium sulfate. Here we have sulfate that is on the border. It's mostly soluble, but there are three robbers, three bandits that make it insoluble. And here's the bandit. Barium is the bandit. So this one is not soluble. This one will be a solid. And then finally, lead chromate. Now, we didn't really say anything about chromates, so we'll assume they are not soluble, unless you would have, for example, a group 1 metal ion with them. So since this lead is actually one of the robbers, it's a good chance that it's not soluble. This one is not soluble. It's a solid. Now, I went pretty quickly through that. I want you to go ahead and try to look through the solubility rules and make sense why we said these are not soluble. These four are not soluble, but these are. Go ahead and look through the solubility rules to make sure you understand why. And then try a few yourself. Okay, so we're going to finally finish talking about how these solubility rules apply in precipitation reactions. Precipitation reactions, remember, are reactions that result in the formation of a solid, a precipitate. A precipitate is actually one of these insoluble solids that we've talked about using the solubility rules. So, and these are double replacement reactions. So an actual reaction, looks like something didn't show up. Here it is. This double replacement reaction that we've seen before is actually a precipitate reaction. And this compound here, silver chloride, contains a group 17 with a robber, which makes it a solid. And that's how we can say that this compound is now a solid, and that's how we can call this a precipitate reaction. The insoluble silver chloride is the precipitate, and that's how this applies, how these solubility rules apply to these precipitation reactions. And actually we're going to do some example problems to show you how that works and wrap up the video. So here it says identify the precipitate that forms when the two solutions are mixed, and then write a balanced equation. So because these are double replacement reactions, we're simply going to replace the first two ions. So calcium replaces ammonium, and you get yourself calcium carbonate. Now when you get calcium carbonate, you get one of each, because remember when you're writing these you have to think about the charges. So calcium has a +2 charge, carbonate has a -2 charge. That's why you need one of each. And then when you write ammonium chloride, ammonium has a +1 charge, and then chloride has a -1 charge. Let's try again. So they match up, and you get yourself ammonium chloride. Now what you do at this point, so we've done this before, this is nothing new, but now at this point what you do is you ask yourself, based on the solubility rules, are these soluble or not? So for example, you ask yourself, is ammonium chloride soluble? Well, because of the presence of ammonium, which is always soluble, no exceptions, this is aqueous, this is soluble. However, here you have a carbonate. We didn't mention carbonates as being soluble unless it's with a nonmetal, unless it's with a group 1 or something. So in this case, based on the rules, this is a solid. And so we see the precipitate. So we've identified the precipitate. So this is the precipitate here. And we've actually written an equation. If this and becomes a plus, we've just written the equation for the reaction. Notice, by the way, on the left side of the arrow, the compounds will always be aqueous, and you have a no exception ammonium in there. So that one is aqueous. Calcium chloride is aqueous based on the rules. On the left side, you'll always see them be aqueous. That's kind of the idea. And the way you find the precipitate is you find, based on the rules, which one is a solid. Let's try the same thing for B. So sodium acetate, now because of the presence of sodium, this is always aqueous. And copper sulfate is also aqueous, because copper is not one of the bandits or the robbers. So you always see them be aqueous on the left. This again is a double replacement reaction, so the copper will come in and replace the sodium will come in and replace the copper. What you'll get is you'll get yourself copper acetate, and the way we write copper acetate, now copper has a +2 charge here. That's because sulfate is a -2. So when copper, I said +2 charge, so when the copper comes on the right, it'll still have that +2 charge. Now when copper has a +2 charge, you need 2 acetates, because each acetate has a -1 charge. Acetates are -1, so you have 2 acetates like this. And then you get yourself sodium sulfate. Now the way you write sodium sulfate, I'll go ahead and write it down here, is Na2SO4, because sodium is +1, sulfate is -2. So here you have your 2 products. And we'll do the same thing we just did up there, asking ourselves, are these soluble? So if you take a look, here we have an acetate that's always soluble, no exception, so we'll put a little AQ on it. Here we have a sodium, which based on the rules is always soluble, no exception. This is also aqueous. What you've seen is we began with 2 aqueous, we ended up with 2 aqueous. What we have here is actually no reaction. And this is the first time we come up to an equation that you can't really write the products of. You really should not be writing these products, because there are no products. This has no reaction. And these solubility rules allow you to predict these reactions now that have, there are no reaction for them. And it's logically possible for you to mix 2 chemicals and nothing happen. We know this is definitely possible, and that's what we're showing you here. Okay, go ahead and try this one on your own, the practice problem, and then we will continue on with molecular net equations in the next video.